for being here. This is the third phase of our four-phase senior thesis conference for Gemstone program. Really appreciate you being here, being supportive of where we're going, and help us celebrate the hard work and blood and sweat and tears that went into a Gemstone thesis project. And these seniors are really going to show you what they've accomplished the last 4 years. It's really tremendous. I'm Dr. Frank Cole. I'm the director of the Gemstone program and also a professor in environmental science and technology here on campus. It's really been my pleasure to help do a small part to guide these students to what they've achieved. They've done it with a lot of work on their own and with the guidance of their support crew, which we'll introduce a little bit later on. But with that, I'll tell you how we're going to operate this. We'll give them about 25 minutes to present their findings. 4 years into 25 minutes. And then we're going to give our distinguished panel of experts here about 10 minutes to ask us some really good zingers, really good questions. And then we'll give the general audience about 10 minutes to ask questions that might come up. And then our students and the experts are going to retreat to a room and have about an hour of friendly chit-chat about their thesis. And maybe learn a thing or two along the way there. So with that, we're going to go ahead and get ready for team pressure. Wow. Go ahead, Professor.
Good afternoon. I'm Catherine. This is Austin and me here, and we're representing Team Pressure. So Team Pressure spent the last 3 years researching wind-induced vibration energy harvesting using piezoelectric transducers coupled with dynamic magnification. Our presentation today will go through the background research for our project, and then we will discuss the 3 subsystems that make up our wind energy harvester, the integration of those 3 subsystems, and then our conclusions from our research. So over the past 15 years, we've seen an increase in CO2 emissions across industries in the U.S. A majority of these CO2 emissions stem from the use of fossil fuels, such as petroleum, natural gas, and coal. Renewable energy only makes up 8% of all of the U.S.'s energy consumption. And of that 8% wind energy, it only makes up 9% of the renewable energy sources utilized. So our research started from an interest in increasing the utilization of wind energy as a renewable source. Piezoelectricity is a feature commonly found in materials such as topaz and quartz. And upon the deformation of a piezoelectric material by mechanical stress, an electrical charge is produced. The unique property of piezoelectric material made it an interesting option to research for use in a wind energy harvester. As you can see from this figure, piezoelectric material has a long lifetime and a low cost per watt compared to other technologies typically used in energy harvesters. Therefore, it's a viable option for an environmentally and economically sustainable wind energy harvester. So our research question and hypothesis going into our 3 years in Gemstone was how can the components of the piezoelectric harvester structure, energy conditioning circuit, and the energy storage system be modified in order to maximize the magnitude of energy stored. And our team hypothesized that if the components of each subsystem are experimentally determined based on the highest performance, then the integrated product will be able to generate and store the most energy. So now I'm going to pass it off to me here, who's going to discuss the harvesting subsystem.
Thank you, Catherine. The research goal for the harvesting subsystem was to create a dynamically magnified wind energy harvester that uses piezoelectrics to generate electricity. The main 2 concepts involved in our research were vortex shedding and dynamic magnification. So within this subject of vortex shedding, the Struwwell number is a dimensionless parameter that helps describe the oscillations of a particular shape in the presence of some kind of flow. So in the case of a cylinder, the structure oscillates up and down in this periodic motion, and vortex shedding refers to this characteristic wave pattern of flow that sheds off the surface of the cylinder on the opposite side. So using the Struwwell number, we can find the shedding frequency for the flow around the structure for a given flow speed. And if we tune the system so that the shedding frequency aligns with the structural frequency, then the entire system experiences greater vibrations. Dynamic magnification magnification describes a phenomenon found in energy harvesters. And one of the simplest energy harvesters is simply a cantilever beam with piezo bonded to its surface. And this piezo generates some voltage when the beam oscillates. One way to add a secondary system is to insert this beam into a cylinder which is fixed on its opposite end, and then place the cylinder in some kind of flow. So when the cylinder oscillates, the inner beam also oscillates. But the two systems are coupled, so there won't be much magnification. However, if you add springs or some kind of elastic material to join the two systems together, the secondary system, or the cylinder, amplifies the primary system, or the beam. And the mass of the plug to which the cantilever beam is attached also plays a large role in this amplification. So here, the stiffness of these springs, or of these elastomers, or the mass of the plug to which the beam is attached, can be adjusted to magnify the output from the piezo. The methodology for the harvesting subsystem included several steps. The first of these was to research the best piezoelectric materials. And for the scale of our project, for the types of voltages that we needed, we found that ceramic PZT5H was the best option. The next step was to gather wind speed data for the Maryland campus and for our testing environment, which was the wind tunnel inside the Cameron Engineering Building. And specifically, we analyzed the correlation between the fan frequency and the fan is what generates flow inside the wind tunnel. So the correlation between fan frequency and flow speed within the wind tunnel test section. The next step involved designing and constructing the harvester itself, both for an option for dynamic magnification and the baseline configuration. The next step was to perform finite element modeling on the structure to predict how the structure would vibrate in different cases. And the next step was to verify this finite element modeling by finding the natural modes of the structure physically by using a laser barometer and a mechanical shaker for vibrational excitation. And I'll go into more detail about these steps shortly. And the final step was to test the energy harvester itself within the wind tunnel environment to determine real-world applicability. This image shows a CAD rendering of the harvester. So on the right side, you see a 3D printed base, which serves as the fixed end of the secondary system, and it also serves as a sleeve for the outer cylinder. And this base actually serves as a mount for the wind tunnel test section. On the opposite end, we have the fixed end of the primary system, which is a cantilever beam mounted to a 3D printed plug. And closer to the plug end of the cantilever beam, we have 4 patches of PZT5H mounted to the surface. And this plug fits snugly inside the cylinder with a rubber elastomer that adds dynamic magnification to the system. These animations show the results of the finite element modeling, or FEM, for the baseline configuration of the harvester. And each animation shows a different natural mode of vibration for the inner beam. And these allow us to predict the vibrational frequencies at which the beam's oscillation will take specific shapes. The first 2 modes are at 9 Hz and 34 Hz, and the third mode is at 76 Hz. For the dynamic magnification configuration, the first 2 modes remain the same, while the third mode increased by 2 Hz. In order to verify this finite element modeling, we devised a setup to physically find the modes of vibration for the system. So this involved using a mechanical shaker to excite the system at a large range of frequencies to determine the locations of the natural modes of vibration for the system. Then we zoomed in on each of these frequencies, zoomed in on each of the modes, and used a laser vibrometer to analyze the shape of each mode. And the vibrometer works by projecting a laser beam on the surface of our cantilever beam and measuring the displacement rate at each point within a specified region. So this is the reason that you can see white tape applied to the beam. This white tape allows the laser to scan the entire surface and create a color map that shows the shape of the displacement at specific frequencies. So in the end, all this data combined allows us to determine the accuracy of the FEM. The graphs on the left here show the physical vibrational responses from our system, which I just explained we did using the shaker and the vibrometer. And on the right side, you see the FEM results. Although it appears that the first, second, and third modes for the beam are slightly shifted to the left when compared to the FEM results, we believe this is a result of the coupling of the system and some unknowns in that respect. But what we're primarily looking at is the aligning of the third mode of the beam and the first mode of the outer cylinder. For the dynamic magnification results, you can see that the third mode of the beam and the first mode of the cylinder are starting to align. The images here show the results of the vibrometer testing. The bottom three images show color maps of what the beam physically, of the way that the beam physically vibrated at each of the first three modes. And we can see here that the vibrometer color maps accurately represent the final model. The final step was to test our system in the wind tunnel. And you can see here that the base serves as the mount for the secondary and primary systems within the wind tunnel test section. So the results for the wind tunnel testing are shown here. And in the baseline configuration, you can see that the Struhl frequency is around 100 Hz at a flow velocity of 20.6 meters per second. And the structural frequency is around 55 Hz. But at the optimal flow speed of 13 meters per second, the Struhl frequency aligns with this structural frequency, and the system experiences its highest levels of vibrations. So, in other words, the first bending mode of the cylinder, which is excited at the Struhl frequency, matches the third bending mode of the inner beam. So, for the baseline configuration, the system experienced a peak voltage of about 440 millivolts, and for the dynamic magnification configuration, we tested two different elastomers. For elastomer A, the peak voltage was about 900 millivolts, and for elastomer B, the peak voltage was about 940 millivolts. One thing to note is that the optimal flow speed for the dynamic magnification configuration was about 19 meters per second, while for the baseline it was about 13 meters per second. So in conclusion, we were able to conclude that the vibrometer verification testing was successful, in that we were able to see the color maps match the FEM. Also, dynamic magnification resulted in more than double the voltage output from the baseline configuration. However, the harvester design was in the end limited by the dimensions of the wind tunnel, and scale was really a limiting factor here in the effectiveness of the harvester. So further research could utilize more piezoelectric materials by either increasing the number or the size of the harvesters. And this would lead to a greater voltage output from the harvester for the conditioning subgroup to rectify. So now I'll hand it off to Austin to discuss the conditioning system.
Thank you, Mika. So the goal of the conditioning subsystem was to determine, convert the AC voltage from the harvesting subsystem into a DC voltage that can be used by the storage subsystem. In this figure, you can see that there's a lot of energy lost in the harvesting and conditioning processes. So our goal is to minimize the energy lost in the conditioning process so that we can maximize the energy we send to the storage subsystem. So an important part of our subsystem is AC-DC conversion. This is accomplished with the bridge rectifier. A bridge rectifier converts any negative portion of the voltage signal into a positive signal using diodes. However, this does not create a smooth output of flow. To solve this problem, we can attach a capacitor to the rectifier, and you can see in the figure below the bridge rectifier the voltage generated by the voltage without the capacitor is shown in pink, and the voltage with the smoothing capacitor is shown in black. And when the voltage from the piezo is less than the voltage coming the voltage across the capacitor, then the capacitor discharges. And when the voltage is greater than the capacitor charges, this can cause the variation in the output voltage to be much smaller. The parts of the circuit that we vary in our testing are the resistance of the load as well as the capacitance value of the smoothing capacitor. To measure the effect of these variables, we look at the output voltage and output power from the DC output signal. For our procedure, we first developed circuit models for the piezoelectric element and our conditioning circuit with PSpice, where the circuit simulated software. After testing the circuits with PSpice, we then built and tested them in the lab. And for our experimental testing, we used the piezoelectric element driven by a mechanical shaker to better control our input voltage. Finally, we compared our experimental and simulated results. This picture shows the circuit model we used to model the piezoelectric element in PSpice. On the left is the theoretical model, and on the right is the actual circuit with part numbers that went into PSpice. The first four parameters in the table area in the green box is the bridge rectifier, and the area in the blue box is the smoothing capacitor and resistive load. This is the primary circuit that we use for our testing. The second circuit we tested was a synchronized switch harvesting on inductor parallel version, or SSHIP circuit. This circuit contains the SEH circuit that I just showed you, the blue and green boxes at the top right. However, the difference is that the circuit is connected to an inductor with a voltage switch at the input. This switch detects when the input voltage has reached a peak and then dumps current into the inductor. This should theoretically improve our performance. However, the switch consumes power, and this may have to be factored into our net power output. This image shows our physical implementation of the SEH circuit. It's the standard diode rectifier bridge is used to convert AC/DC input is shown on the left of the figure. You can see the smoothing capacitor to the right of it, and the resistive load is replaced by a resistor box, so we can easily sweep the value of the load resistance. The green wire leads to a data acquisition device, or DAC, which was used to measure the output voltage of the motor. This is an image of our experimental setup. You can see the mechanical shaker and piezoelectric element used to create the input voltage at the top. And we used the piezoelectric element on the beam that was closest to the root of the beam to provide the greatest power. And we tuned that force from the shaker to provide 4 volts peak to peak as in the simulation. The piezoelectric element is connected to the input of the SEH circuit, and the output is connected to the DAC, which connects to a computer via USB or a port or data. We measured the voltage across the resistive load while varying the value of the resistance for 4 distinct values of the smoothing capacitor. These graphs show the simulated experimental data for these 4 values in the SEH circuit. Our results showed a similar behavior between experimental and simulated data for all capacitance values. However, the simulated voltage was higher than the experimental voltage in all cases. The graph on the left shows the output power of the SEH circuits. This is calculated using the voltage that I showed you in the previous slide. The table on the right shows the peak power and its corresponding load resistance for each capacitor value. Our data shows that peak power existed for each circuit as expected, and you can see in the table that the load resistance and peak power from the experimental data was consistently low in the simulated data. So while we did most of our testing with the SEH circuit, we still wanted to compare the SEH circuit to the SSHIP circuit. These graphs show a comparison of the simulated power and voltage curves for both the SEH and SSHIP circuits. Initially, it seems like the SSHIP would perform better than the SEH due to the higher voltage, which doesn't level off as quickly as the SEH. However, in almost all cases, the net power for the SSHIP is negative due to the power consumed by the active components of the circuit. In conclusion, we found that the change in peak power caused by using a different capacitor was at most 0.03 microns. This was true in both the experimental and simulated data. However, we saw an overall loss between the experimental and simulated data due to real-world losses that were not accounted for in the simulations. Optimal resistance values were also worse within 100 ohms for the simulated set and within 600 ohms for the experimental set. This tells us that for low-frequency applications such as ours, our simulation, driving the capacitor value does not have a large effect on peak power. From the simulation results, we can accurately predict an optimal impedance level within a small range. And this is useful for selecting an optimal storage system. However, we can't yet accurately predict the amount of power that will be produced, because our model does not include real-world losses. Finally, although the SSHIP could theoretically create more power, for our scale, we saw the SEH outperform it. With a more efficient switch design, it's possible that SSHIP would outperform the SEH. And now I'll hand it off to Catherine to talk about the storage system.
Thank you, Austin. So the goal of the storage subgroup was to determine the most efficient storage device that could charge with the low input we were receiving from the conditioning subsystem and power load at a higher voltage. So our methodology consisted of 3 main steps. First, we designed our printed circuit board for the microchip that we chose. We placed all of our breadboard components for each experimental setup. And for our experimentation, we had 3 different setups. We used 2 different lithium-ion batteries. Sorry. One was a 3-volt lithium-ion battery, and the other was a 4.1-volt lithium-ion battery. And then we also had one experimental system where we coupled a lithium-ion battery with a supercapacitor to make a hybrid system. And on the slide, you can see the specs for our 4.1-volt energy battery. So because we were receiving a very low input from the conditioning subsystem, we needed to investigate a way to boost that charge up so that we can effectively charge our battery at the right voltage. So we chose this microchip, and the microchip uses a boost regulator to support low voltage sources as low as 0.48 volts. So the target battery for this microchip was a 4.1 volt energy battery that we used. And we created a printed circuit board for our testing so we could easily exchange out parts on the breadboard. Here you see our setup. The rectangle is the microchip, and then on the left in the yellow box, you see the source that comes from the conditioning subsystem. In the red box, that's the boost regulator, and this combines components that are exterior to the microchip as well as within the microchip. And it allows for charge to build up at the charge pin until the voltage is at the correct level for the battery. Then the battery charges, and the PCK key pin on the right-hand side of the blue box regulates the output to the load. We used a quick test to test the efficiency of each of our systems. And the quick test, you start your battery at a voltage V0, and you record the time to charge your battery up to a higher voltage, V1. Then you allow your battery to discharge, recording that time to a voltage below your original V0. And then you recharge your battery, recording the time once again up to your original V0. And with all of these numbers, you are then able to calculate the efficiency of your storage system. What it really comes down to, though, is looking at the discharge energy divided by the charge energy. So in the end, we were able to control the charge and discharge of our 4.1 volt energy battery with our 1 volt input and an LED and resistor as our load. In the beginning cycles of the Thenergy battery, we found that it had approximately a 90% efficiency, and this high efficiency would be expected in those beginning cycles of the battery's lifetime. In conclusion, the storage subsystem designed control circuitry for charging and discharging of the 4.1 volt energy battery. Mismatches between the voltage ratings of our battery, microchip, and supercapacitor that we originally chose for our testing caused some damage to our storage system. The lithium ion and supercapacitor hybrid system did not end up working in the end because it required a DC to DC converter. But our boost regulator harvesting chip was an adequate chip for us to use for charging with a low voltage source. So now I'll hand it off to Austin, who will talk about the integration of the 3 subsystems.
Thank you, Kevin. The final phase of our testing was to integrate all our subsystems in scalable form by connecting the harvesting to the conditioning subsystems and the conditioning subsystem to the storage subsystem. Here you can see the experimental setups for all of them, for all the subsystems. So the research goal for this phase of testing was to determine the maximum power output from the integrated harvesting conditioning subsystem and determine how rectified energy was able to be stored in the conditioning storage system. For our harvesting conditioning system, we first determined an optimal fan flow speed for baseline configuration of the harvesting subsystem. And the optimal fan flow speed is the fan flow speed that will produce the highest voltage for the harvester. We then connected the piezoelectric harvester to the input of the SEH circuit, and then we measured the rectified output voltage at that optimal fan flow speed. We generated an output of 350 millivolts AC at the optimal fan flow speed from the harvesting subsystem, but we only produced an output of 30 millivolts DC. We believe that the 30 millivolts is actually a result of the internal bias of the DAC device and has no relationship to the actual input voltage. This is because we swept the load resistance and saw no change in the 30 millivolt value. We believe that 350 millivolts is insufficient to pass the diode bias voltage. For the conditioning storage system, we generated a 4 volt peak-to-peak input to the conditioning circuit with a mechanical shaker and piezoelectric element. We then connected the DC output of this SEH circuit to input 5 volt CC. This was likely due to the impedance mismatch of the storage and conditioning subsystems, and this voltage was insufficient to charge our battery. So in conclusion, for our integration testing, we found out that the energy harvesting design was, the fact that the energy harvesting now was limited by the dimensions of one tunnel hindered our integration testing. This insufficient voltage on the harvester propagated throughout all our subsystems. And for further research, we would integrate our subsystems at the beginning of our testing and then focus on shaker testing so we could better control the energy output. In conclusion, we successfully demonstrated a dynamic magnification in the harvesting subsystem, and we were able to successfully predict the optimal load given these electric using simulations, and we were able to design a storage system for low voltage applications. We would like to thank our mentor, Dr. Boz, and his graduate students, our librarian, ACCIAC, the Maryland Sustainability Fund, and all our family and friends. Any questions?
All right, I want to thank Team Fresh for a tremendous presentation. Clearly, they've done a tremendous amount of work, and hope everyone will follow along with every little detail of it. Before we go into the questions by the discussant, Dr. Ross, I'd like to stand up, please, to the team's mentor. I want to thank him for all his efforts. Now on to the questions from the team discussants. I'll ask each discussant the first time you ask a question, introduce yourself to the audience, basically why you're an expert in this area, briefly, no resumes, please. And then we'll ask the question, we'll get about part 10 minutes, and then we'll go on to open questions from the audience. So who wants to go first? Okay, great.
I'm Young Yu from Mechanical Engineering Department of the University of Maryland. So I want to ask you a question about your dynamic magnification. So how you design this whole structure to actually magnify the vibration of this beam. So I mean, how you design the software and compare, for example, the stiffness or the dimension or whatever, the parameters, how you come up with those parameters.
Not all at once.
Our original material selections were based on availability materials. Our cylinder and our elastomers we got from McMaster Car. So we were limited in the stiffness and the size of those materials, and also limited by the wind tunnel. But we had multiple elastomers that we originally used for the prototype fabrication. And after we saw the FEM models created in help with the assistance of our mentor, we were going to choose the best elastomer for the cylinder dimension that we used, and also for the wind tunnel dimensions that we had. So it's all about tuning those geometric properties with the freedom that we had to tune. We had a set cylinder size and a set length that we could use in the wind tunnel. So it's mainly tuning that elastomer stiffness to optimally magnify the system and align that third node of the beam with the first node of the cylinder. Does that answer your question?
Okay, thank you. We'll go next. Yes.
What were Norman Worley from Aerospace Engineering? What were your criteria that you used to place the pieces on your beam?
So we wanted to generate the maximum strain from our piezo. So the obvious location of the beam is to put it as close to the plug as possible, because that's going to be our maximum deflection in both the first and the third modes of the beam. So wherever we saw that maximum strain, the maximum deflection of the beam was where we were going to put the piezos. Obviously, with further testing, we could add more piezo to increase the voltage, but as you move farther from that plug, and as you stack piezo higher in the beam, you're going to get diminishing returns because you get farther from the center of the beam, and also farther from that area of high strain.
Okay, next.
Hello, I'm Tim, Coach of Mechanical Engineering. This will probably be a presentation. So the question for you based on your work is how one uses the device and how actually beyond the steps.
Practical application.
Initially, at the very beginning of our research, the main real-world application we were projecting was to use this kind of system in a light pole. So, for example, if you have a light pole on campus and it experiences any kind of flow, any kind of wind, then if you have these kinds of structures inside and generate some kind of voltage, you can store that voltage in a battery, and that battery will power any nearby electronics, maybe even the light.
Okay. Oh?
Oh, I don't.
One of which is from a research lab don't get electrics. So one of the questions I have is, given the frequency range you guys in targeting, did you guys consider magnetic materials incorporating magnetic and electrics as well as potentially in a hybrid solution?
Question was regarding the use of magnetic materials in addition to piezoelectric. We initially were planning on using a combination of PCT and UPDF films. We didn't want to complicate it further by going beyond piezoelectric materials because we already had a lot of systems to work with, so we focused on the PCT and the magnification of those piezoelectric films.
Okay.
My name is Johan Larson. I'm from the Mechanical Engineering Department. I wonder if you build one of these with fixed dimensions of materials, what kind of speed range will it be effective? Or will that be a very narrow range or a broad range? And have you thought about ways that might be important in this program?
Yeah, so this question was about the geometry and how it limits us in our ranges of effectiveness. So you saw in the plots showing the energy that we saw in the wind tunnel is that our peak was at that very specific wind speed. But we're obviously harvesting energy from the whole range of wind speeds that we tested. It's just not maximized unless we're at that speed. We're able to, in future research, we might be able to electrically tune the device to be more useful on a wider range of wind speeds. But for the limitations, both time and financial for the project, we're only able to use our fixed dimensions. But that's definitely a future direction that we'd be interested in extending.
Okay. Yes, sir.
Robert Burley, U.S. Army Research Laboratory, and my background's in electronics engineering. One question I had was, I know it was very good work. What consideration did you guys give initially to top-level input-output constraints? And then as you progressed, were you able to adjust those at all as you saw different output voltages coming from each of the levels?
So the question was, what type of considerations do we give to kind of input-output considerations when we're consuming the electrical components?
Yes.
So initially, when we did kind of research into the types of scales for voltages in the input, especially if it's low frequency application, we saw anywhere from, like 0.1 to 5 volts. So that's the initial target for the voltage. And specifically, the initial feedback, because the way we kind of did our research was in stages. So the initial feedback from the harvesting group was that we would see anywhere from 0.3 volts to 1 volt. But that proved to be kind of difficult to test in the conditioning circuits. So for the conditioning circuits, we chose a voltage of 2 volts, specifically the type of diodes we chose, which resulted in at least a 0.7 volt drop. In terms of the output, that was kind of limited at least from the conditioning circuit. The output was limited to the input, the charging circuit, which I think requires at least 0.7 volts in order to be effective. So those were kind of the overarching concerns we had.
More discussing questions? For a second round. If not, I'll open up to the general audience now. Anyone else have a question they'd like to ask? Peer pressure.
First off, I'm absolutely blown away by this. I can't even describe it. It's just so amazing. But my questions are, I have two. What do you plan on doing with this product now that you've made such an incredible and innovative device? And under ideal conditions, how long will it take for this device that you've made to charge my iPhone?
So in terms of future directions for the project, I think this is really important for the underclassmen in the program, is that we learned a lot about realistic expectations for the project. freshman year, we were like, we weren't planning on job hunting. We thought we'd have a company by the end of this. We're talking about like patent research, and obviously with the challenges that we faced, we weren't able to reach the level that we expected with our output in terms of on-campus testing. But I think with the research and the groundwork that we laid in terms of the modeling, there's a lot of room for improvement for either other GenSo teams or future researchers to improve on the technology and to use our models to better understand the constraints of the project and the challenges of the field. In terms of the iPhone charging, it's going to be pretty hard to comment on that based on the low voltage and current that we were getting out of our system. But obviously with a larger scale system, not limited by the wind tunnel dimensions, the possibilities are definitely there for something like a charging station or a streetlight application as we talked about earlier.
Very good. Other questions from the audience?
Hi. There was nice work on matching the electrical needs to extract the right amount of power. I was wondering, I didn't really see how you matched the mechanical impedance to directly couple the piezo to the source so that you actually get the most out of it. And if you do, then when you start extracting electrical, you're going to change the damping of the beam, so that would have been something else in the model. So did you do all that?
Yeah, so the question was essentially, correct me if I'm wrong, so it was how did we kind of factor in the mechanical components of the physical harvester and the piezo in terms of impedance matching? Yeah. So in one of the slides where we kind of touched on it briefly, the model that we were using to model the piezo modeled both the electrical components of the piezo as well as the physical. So some of the properties we were looking at were like the compliance of the piezo, the stiffness, and all these things. And so when we actually modeled that in DSpice, and with the help of as well a transformer, we were basically modeling the combined impedance of the electrical and mechanical stress on the whole system. So any type of impedance matching we were doing matched both the electrical impedance and the actual mechanical impedance as well.
Okay, great. More questions from the audience? And I'll come back to discuss this in a moment. The audience questions? A burning question I want to ask them up here discussing? I want to say it before we go into a private room. All right, I think that looks like we're wrapped up. Whoa. Yes, sir. Yes, sir. Amen.
I just want to say a couple of words for this James School program. Fantastic help that we got from Frank and Kristen. I don't know where she is, but I like to thank the other group. There's both of them, and their office done a fantastic job to make the life of these 14 guys here fantastic, and made me my job very easy to harvest the energy. And 3 years. And they look very quiet here, but you should see them in the lab, they're very loud. Second thing I'd like to thank all the members of the community, because all of them are very busy and they're very generous to come and participate with us here tonight. Thanks again, and thanks for all the pressure. Yeah, fantastic.
Thank you for that. It's a real pleasure working with these students, and for family members in the audience, you all should be really proud about who they are. So this is what we're going to do. Everyone's going to sit still. No one's going to move.